Good afternoon. Right. The time is up, sir. I said 3 o'clock already. I will accept no more submissions, okay? 3 o'clock, the time is up. I ask you guys to submit as early as possible. Seems hello. 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 Shh. Can you guys hear me from the back? Hello? Yes? Okay, good. Oh, come on, you're late, sir. It's already 3 o'clock. It's all right. Okay, not next time, okay? Thank you. Yeah. I asked you guys to submit as early as possible. It seems that most of you are submitting very late in the last hour. That gives me a lot of work because, you see, I have to mark most of you after I return to my room. Anyway, I will try to return your scanned work tonight, okay? So check your email. Keep checking your email. Right. Now, today, I'm going to talk about, before I start talking about anything, quiz 3 is due next Monday, right? So please don't be late, right? And make sure that you do write down your ID and the full name. I've seen scripts with only the ID number but no names, and sometimes only the name but no ID number. So please, in the future, please write your full name and your ID, right? Okay. Now, before I start, let me revise what we did last Thursday. This is stuff we did. The stuff we did last Thursday. Remember, the Thursday lectures are held in Roscoe Theater A. We started talking about the normal distribution. The normal distribution is also known as the Gaussian distribution. It's given by this PDF. This is the PDF of the normal distribution. There are two parameters, mu and sigma, and this is the notation to mean that a variable x has the normal distribution with parameters mu and sigma, right? Then I talked about the CDF of the normal distribution, which is given by this formula here, right? Sorry. This is the formula for the CDF of the normal distribution, where phi, capital Phi denotes the CDF of the normal distribution with 0, mean, and variance 1. If you are using R, use D norm to compute the density of the normal, PDF of the normal, and P norm to compute the CDF of the normal. Right? Then I talked about some properties. These are 5 properties I mentioned last Thursday. So the mean of a normal variable is mu, the variance is sigma squared, the standard deviation is sigma. Any linear combination like this, ax plus b, will also have a normal distribution. In particular, this linear combination here will have this distribution, which is n01, or 0 mean and variance 1. It's known as the standard normal. It's known as the standard normal distribution, right? Then I talked about two more complicated properties. The first one is that if you have two independent random variables, x1 and x2, both normally distributed, then any linear combination of the two also has the normal distribution, right? And in general, if you have p can be any number, 2, 3 million. If you have p independent normal random variables, then their linear combination is also a normal variable, right? This is a result I mentioned last week. If you have a random sample, you know what the word random sample means, right? Don't get it wrong, okay? The random sample, if you have a random sample from a normal distribution, then the parameters mu and sigma can be estimated by this and this. So mu can be estimated by the sample mean, and sigma can be estimated by this, right? This is a result that can be actually, all the results I mentioned so far, can be proved, but that's beyond the scope of this course I'm teaching you now. When you move to year 2, you will know how to prove these things, right? Right. Then I did a couple of examples. This is the first example I did. Suppose you have a variable x that has this normal distribution, and you want to find the probability that x is less than 2, then you do it like this. Where phi, as I said before, is this CDF of the standard normal, right? And it can be read from a table like this one. I think this is a table I showed you last week, right? This is the second example I did. This is example example 2, right? So where we computed the probability that a variable x is greater than 3. It's the same procedure as before. You normalize x by subtracting the mean and dividing by the standard deviation, both sides. Then you get this. You can write this as this by the complement rule. And finally, you get this. And you can read phi of 1 from the table to get this, right? Let me do some more examples today before I move on. Let me do some. Come on, guys. Let me do some more examples, right? So this is example. Can you see this now? Okay, here we are. This is example 3. All right. Suppose x is a normal variable with parameters 1 and 4. And we want to find, suppose we want to find the probability, say x is minus, suppose we want to find the probability that x is less than minus 1. Okay? And in this case, okay, the first thing we do as usual is to you subtract the mean You subtract the mean on both sides and divide by the standard deviation, right? So you get, on the left-hand side, you get the standard normal. That's because of the result I mentioned last Thursday, right? Remember, when you subtract the mean and divide by the standard deviation, any normal variable will reduce to standard normal variable, right? And on the right-hand side, you get -1. So this is phi at -1. Now, there is a result which I did not mention last week, is the following. The result says the following, that if you have something like phi at -x, right? If you have something like x minus in front of it, then there is a fact which says that this is the same, this is the same as, this is a known fact, right? This is true because of the fact that the standard normal distribution is symmetric around 0, all right? That's why this is true, right? So we can write phi at -1 as, using this fact, you can write it as 1 minus phi 1, okay? And now if you read the table, this is a table I showed you last Thursday. Where is phi 1? Phi 1 is here, right? This is, and you read it, guys. I mean, I know it's too small for you, but can you see it now? Right? If you go along this row or so column, you see you hit 1 here, and then you look for 0, so you get 0.8413. So this is 1 minus 0.8413. All right, guys, it's easy, right? So sometimes you have to use this fact to compute normal probabilities, right? So, all right, next. You don't need to copy this down, guys. So, okay, just one more example. Example 4. Suppose right? And we want to compute, suppose we want to compute the probability that all right, suppose we want to compute the probability that x lies between -1 and +4. So in this case, this is a two-sided inequality. All right, so yeah. All right, you see what I've done? So this becomes this, yes? Now, this you can write as you can write this as the difference of the two probabilities, yes? Now this is phi, come on guys, are you okay guys? Huh? you okay, sir? Hello? Sorry. Yes.
You can turn the heating down.
I don't put the heater, man. I don't put the heater. I don't know where the heater is. Okay. It's only 1 hour, man. So it's not bad. Okay, shh. Listen, phi at -1 can be written as right? Are you guys with me or what? Now, if you read the table, here we go again. You should read the table. Phi at 1.5 is 0.9332. So 0. I mean, you guys have a copy of the table in front of you. Okay, and phi at 1 is this, right? So that's the answer, right? I mean, if you have a calculator, you can compute this. You see what I've done or no? Any questions? You okay? All right. Are you right, sir? Yeah. Was this true? Okay. Okay. All right. The next thing I'm going to talk about is the remember the normal distribution is for continuous data, right? The binomial distribution is for discrete data, right? So the next thing I'm going to talk about is the binomial distribution, right? I'm sure all of you know the binomial distribution, right? This is the probability mass function of the binomial. So k goes from 0, 1 up to n. P is a number between 0, and 1, right? Are you guys okay? Is it too hot for you? I'm sorry, I can't help, but I wish I knew how to cool down. All right, so n is known as the size parameter. And P is known as the probability of success. Okay? All right, guys? We write normally, if a variable has a binomial distribution, we write x this is the notation that I will use, right, to denote a variable that has a binomial distribution, right? Okay? And, okay, so the next one. The CDF of a binomial random variable is given by the following. All right, this is the CDF, right? And the R command in R, right, you write right, this command here will compute the PDF, right? And the following command, pbinom, P, B, I, will compute the CDF, right? Okay, guys. So this is the command for computing the PMF. Sorry, I should say a PMF, not PDF, PMF, because we are dealing with the probability mass function, not a continuous variable. So it will compute the PMF of the binomial, and this command will compute the CDF of the binomial distribution, right? All right, guys. Next, some properties. If x has a binomial distribution with parameters n and p, then the expectation of x is n times p, and the variance of x, I'm sure all of this, is n times p times 1 minus p. Okay, so these are two properties. I'm sure you know these properties from probability 1, right? So these are two properties of the binomial distribution, right? Okay? Right, now let me do some examples. Example. Shh. I'll buy you guys some ice cream after this. So just stay with me, please. Okay. Right. Right. Suppose x has a binomial distribution with parameters 5.5, right? And suppose we want to compute the probability that x is less than 1. What would that be?
5, 0.
Remember, x can only take integer values. So if x is less than 1, the only value it can take is 0, right? Okay? And the probability that x equal to 0 is if I choose 0, half, right? You with me? If I choose 0 is 1, this is 1, this is half, so the answer is 1/2 over 5. Yes? Right? So that's a simple example, but let me give you example 2. Example 2, right? Suppose the same thing. Suppose x has the binomial distribution with parameters 5.5. Right? Now, if I suppose I want to find the probability that x is between 1.5 and 3.5. Now, what would this be? This will be the probability, because if it's between 1.5 and 2.5, the only integer values are 2 and 3. So this is the probability that x equal to 2 and the probability that x equal to 3. You guys follow me, right? So this is, if I choose 2, right? I mean, I will let you simplify this. I'm not going to waste my time simplifying this, okay? So these are 2 examples. But now, suppose one more example. Example 3. Suppose right, suppose you want to find the probability that for a variable, binomial variable, that x with these parameters. So suppose you want to say find right? Now this right? Yeah? Suppose you want to find, this is okay, you can compute this easily, but suppose you want to find a probability like this. right? Right, this would amount to computing I mean, these are very big numbers, right? I mean, you can't possibly do this in an exam because it will take you forever to compute things like this. I mean, when you have 100 choose 10 or 100 choose 90, it will take you a long time to compute that in the exam, right? So is there an alternative way? I mean, is there a simpler way to compute probabilities, binomial probabilities, when you deal with big numbers, right? So that's what I'm going to talk about next, right? Is there a simple way to compute binomial probabilities when you deal with big numbers like 100 or 1,000 or million, right? When this number here is a huge number, can you find a simpler way to do things, right? Right, that's what I'm going to talk about now. All right, and to do that, I'm going to talk about something called you guys heard about central limit theorem? Yes, you have. Yes, right. Right, suppose you have a random sample from a population which has mean equal to mu and variance equal to sigma squared. Right. The central limit theorem says the following. Right. It says that this guy here approaches the standard normal variable as n goes to infinity, right? Where x bar is the sample mean. Right? X bar is the sample mean. Right, this is the much celebrated central limit theorem. Okay. All right. Okay. So what we can do from this is the following. We can say we should call this. Let me call this star. Right? Let me, oh, sorry, you can't see it. Let me call this star, okay? So if n is large enough, if n is a large number, right, if n is a large number, then using star we can approximate the distribution on the left hand side by the standard normal distribution, right? So we can say x bar minus mu divided by sigma by root of n has an approximate distribution which is standard normal. Right? You follow what I'm saying? That if n is, let's say, if n is 100 or 1,000 or million, then it's reasonable to approximate this by this, right? Okay. So what we are saying is, this implies, right, that x bar minus mu is approximately, is approximately sigma by root of n is this, okay? Now what, if you multiply a normal variable by a constant, what do you get? Don't tell me you don't know. I mean, this is a constant, right? And your constant multiplied by a random variable, what does it change? Because the mean is 0, so the mean of this is going to be 0 too. So the mean will remain 0, and the variance will become, what would the variance become? It will become sigma squared by n. You follow me, right? Okay, this is stuff we did last week or the week before. All right, so this implies that x bar has an approximate distribution which is mu plus right, and this implies that x bar has an approximate distribution. Now if you add a constant to a random variable, the variance doesn't change but the mean does, right? So this would become a normal. So this is 0, guys, 0. Okay. So by the central limit theorem, we can argue that if n is large enough, n is the sample size. If n is large enough, then the sample mean has an approximate distribution looking like this, right? You follow me, right? Now, one more thing. One more. Now we know that x bar right? Now if I take the n here to the right hand side, all right, now let me ask you that if you multiply n is a constant, right? Constant times the random variable, what would it change? It would change, the mean will get changed to n mu, and the variance will become what? N sigma squared. Okay? You follow me? So the result we have is the following. That, let me write it down neatly. The result we have is that the sum of xi, I from 1 to n, as an approximate normal distribution with these parameters. Okay, now I'm going to use this to approximate the binomial. Now, do you know something called the Bernoulli distribution? You must have done this in your probability 1. Don't tell me you don't know. I know. All right? There's something called the Bernoulli. Now, there's a connection between the Bernoulli and the binomial. Do you know what the connection is? Oh, you forgot? Maybe you forgot that after the probability 1 exam. Huh? Okay, now suppose, all right, suppose this is stuff you must have done in probability 1. I'm not trying to patronize, but I mean, if you look back, you will see. Then, all right, then the sum of xi's has a binomial. I mean, this is a fact. If you look at the handout I gave you the first day, which is the collection of distributions, I'm sure the handout contains this formula, right? Okay. Now we know that for the Bernoulli distribution, mu is the expectation of x is equal to, do you guys remember the formula for the mean for the Bernoulli? It's actually equal to p. If you don't remember, you can look it up in the handout. And the variance, which is sigma squared, is p times 1 minus p, right? The reason I'm writing this is because I'm going to use, let me go back, this is going to be tricky. Let me call this double star, right? I'm going to call the one on the top double star, okay? So by double star, can you see this, guys? By double star, right? This is double star here, okay? By double star, the sum of xi right? Okay, are you guys with me or no? Are you sleeping? I see some of you sleeping. Why? Yeah. So this implies that the binomial distribution with parameters n and p can be approximated by a normal distribution with parameters np and np times 1 minus p. So this is what I was trying to say earlier, that if n is large, like 100 or 1,000 or million, you can approximate the binomial distribution by a normal distribution. And finding the probabilities for a normal distribution is much easier than for the binomial distribution. And I will do some examples on Thursday, but before that, can you please complete the piece of sheet I put in front of you and return that to me? I'm finishing early because to give you time, guys. Guys, please complete the feedback form and kindly return it to me. Thank you very much. you're late, sir. It's already 3 o'clock. Don't be late next time. Okay. What? Oh, thank you. Thank you. Thank you, sir. Thank you. You can put it here, sir. Thank you. Oh, you're late, sir. You're late. I said it's 3 o'clock.
Oh, 3. Oh, sorry.
Come on. I said it's 3 o'clock. It's already 4 o'clock now.
Okay.
But don't be late next time, okay?
Okay.
Okay. All right. Okay. Don't be late next time.
Sorry, I forgot to hand it.
Why? It's already late, madam. So late, madam. You're so late. Independent and identical distribution. Independent and identical. How are you guys?
I'm good, how are you?
Did you fill in this?
Yeah. I've given it to my friend. He's actually just bringing it down with himself now.
Okay, man. All right.
So, can I have us?
Huh?
Cheers.
Oh, sorry, man. Yeah, you can give it to me now. Yeah.
I forgot to write my ID number.
I don't know. Did you write your name?
Yeah.
Yeah, okay, I'll find out.
Okay, thank you.
Find out.
Yeah, I'm fine. Thanks a lot. Cheers. See you.
See you, man. See you. No, thank you, man. Sorry. I'm sorry, you're late already. Okay, I'll mark. Don't be late next time, okay? Don't be late next time. Yeah, don't be. Oh.
Yeah, because heat rises, you fool. That's why I thought you. Sorry.
See you later now.